All right. How's everyone doing? I'm good. Yeah, suddenly the weather got worse. I went for a big run yesterday down on the river, which just so nice. The weather, like we're in the middle of spring. But yeah, nice seeing everyone. Ready for summer?
Yes.
That's the correct answer. So we have a pretty big one today. This, I think, in a lot of ways, is sort of the pinnacle of what we're doing in the class. We're talking about essentially. So we're going to have multiple options that we're choosing, but instead of them being ordered, they're going to be unordered. So it's going to be what we call multinomial choice. This is, I think, the truest extension of the binary outcome framework. There was a Nobel Prize given for the thing we're about to talk about today. This is, I think, one of the core skill sets for sort of the type of thing we're covering in this class. So we'll talk about this for the first part of class, and then we will get to, I think we're going to have time today to cover APIs. So we have sort of a secondary sort of stream that we're covering near the end of the semester here. We have 3 more class periods. Unfortunately, it's only 3. What if we just pushed summer back 1 extra week? Y'all be happy with that? No one would be happy with that, including me. So we have 3 more class periods, and I'm hoping in the last 3 we'll be able to cover 3 sort of like data-specific kinds of things. It's, I think, in a lot of ways, talking about APIs and SQL and where to find data sets is like, I love the core content we're covering in this class. This is like an incredibly powerful thing to know how to work with, and taking a detour into APIs is less interesting, I think. Maybe it's more interesting for you. I can't judge what's more and less interesting, but it's talking about APIs, working with SQL databases. That sort of thing is something, like, it may come up in interviews, and so I think having the skill set and at least having seen it before, not necessarily feeling like totally familiar with these kinds of things, I think would be helpful in like whatever comes next for you. If you're going into a field working with data, which I imagine a lot of you will be. So that's why we cover these things, just to get some extra exposure. They're not, like I said, they're not like incredibly like conceptually that interesting, but they're really powerful skills. So I'm hoping we'll have some time at the end of each of these classes to cover these kinds of things. Okay. So the TV is on, I believe. At least it was. Y'all do anything interesting this past weekend?
I got Taco Bell.
Nice, okay. Is there a Taco Bell? You got Taco Bell too?
I did.
Is there a Taco Bell in the city?
Yeah, there's one near the stadium, well, kind of near the stadium. I don't really know exactly.
Okay.
Manchester, right? It's like a little bit past the stadium.
Yeah.
Yeah, it's out in like Manchester.
Okay.
I went to the one that's through the, I don't know if it was the tunnel. Is it like Swissville or something?
Oh, Swissvale.
Yeah.
Yeah, there might be one out there. Okay.
So that was fun.
That's nice. Yeah. The only time I eat fast food is Taco Bell.
That's my favorite one.
By far. I agree. You also got Taco Bell?
Yes, but I live in the boonies, so
Nice.
it's not in the city.
So yeah, maybe a little easier to get Taco Bell.
Yeah.
I went to art all night.
You went to what?
Art all night?
Oh yes. Let's see. Is that on the south side?
No, it moved. It moves like every year. It was you know where a 7 Point Brews is, or like the Co-op, or
Yes.
it's right out. It was at like the Rockwell Park, one of the warehouses they own.
Okay. That's fun. That's a fun event. My wife volunteered there one year.
Oh, cool. Yeah.
Got the shirt.
Yeah,
Uh,
yeah. We tried to go.
So let's see. We could do this just on a whiteboard if you want. There we go. Maybe it's my technology today. Okay, so I think in a lot of ways this is one of the highlights of the semester for me. This is, I think conceptually, as always with these things, what we're going to do is talk about the high level, like what are we doing with multinomial choice? Why do we, why is this a particularly powerful thing to be thinking about? Then we're going to talk about the math, like the mathematical setup, some of the theory for what we're doing. And then we're going to get into actually coding it up, which unfortunately for today is going to be kind of a slog. We're going to do a simple one using simulated data, and then we're going to look at transit choice, so public transit between Montreal and Toronto, and build a model for transit choice, which we can't do with any of the existing models we have. So we're going to do it with a real data set. But the unfortunate thing is it's complicated enough that I'm going to hand wave my way through a few things just because I don't think it's worth getting into the details of like data manipulations in class. What we're focused on today is thinking about the model, setting it up, and understanding like the core components. So that's where we're going. And then, like I mentioned, at the end of class, I'm hoping to have a little bit of time. I have this whole second page on the website set up for some of the things we're about to talk about with data. I have some interesting examples with APIs for today, so that's going to be found here. We have 3 more classes, 2 this week, 1 next week, and then we have a final exam period, which I'll send out more information about. But that's like what's left in the class.
Will it be like what we've done previously in office hours, or is it like an extra?
Yes. Yep. So it's not going to be handwritten. The checkpoints are intended to be a good indication of what's going to be on the final.
Wait, when will the final exam be?
So it's the way the registrar does this. It's supposed to be during the final exam. During the final class period.
Okay.
During the it's like for undergrads, the next week is the final exam period. We have 1 more class on Monday, and then the final,
Okay.
which is supposed to be during the last class for us.
Okay.
Does that sound right?
I think we
Graduate
graduated
on.
last class.
Yeah.
You
The scheduling of it is so weird. I don't understand why it is.
when
like this.
when do you graduate?
Thursday.
You graduate on Thursday.
Yeah.
Okay, so we're gonna have to push this back a day. So let's see. You're in Randy's class, sort of parallel to this at the moment, right? What's he doing next week? No idea.
Maybe you have a
I don't
final.
think he knows either.
He doesn't have a final.
I don't think we do.
Yeah, we just have our final like capstone presentation on Wednesday, which he's kind of like part of.
Of next week.
Yeah.
Okay. What if we didn't have So what if we moved everything up one day? I'll give you the final at the beginning of next week. Does that sound like a reasonable thing? I'll send out more information about this, but I think we're not going to be, we can be here in the classroom, but this is going to be more like a checkpoint. It's not going to be like sitting down for 2.5 hours and doing a thing. It'll be a little bit more flexible than that. Okay, so that means we're going to have one fewer topic to cover. Yeah, Kevin?
Sorry, do you just mean like make it like a take-home final, basically?
It's going to be more like a take-home, yeah. But I haven't finalized, like, things are a little bit different this semester than last semester, so I haven't finalized all of the details yet, so don't hold me to anything super tightly. But yeah, so think of it sort of in the same ballpark as a checkpoint, just a little bit more comprehensive. And you can't work together, sadly. Okay, any other questions here? Okay, you just got yourself out of one more class period. So whether you like that or not is your choice. Today we're covering, so that means we're not going to get through all of the data sections, unfortunately. And it also means we're not going to cover hazards. And censoring, if we do our job today, will be the last thing we cover. Okay, well, you're going to, you avoided a hazard. Thanks for laughing. I'm training for the marathon, and yesterday was a 20-mile run. So if I'm like a little bit woozy today, my jokes are never good, and today they'll be worse. Okay, so nice. So that's where we're going. 2 more class periods, and then a final. So I was just talking about the multinomial choice framework. The structure for today, we're talking about just the basic setup, and then we're going to get into some complicated versions. Okay, so and by complicated, I don't mean particularly challenging for your level. Just it's a more complicated model than the binary outcomes. Okay, so in topic 08, we covered sort of this, this latent variable idea where we have this y star or an eta, where we have a linear model predicting something that we can't see. All we can see is the choice. So this was the basic idea. Last class, we set up this this model where we have some order, some ordered structure to our choices. So behind the scenes, we have this latent variable. The first way we set this up was with a picture where, on the horizontal axis, we had our latent variable. And then we just had a distribution, and we used different cutoffs. So we were using either the logit or the probit, and then we just had different cutoffs. And so our different regions represented different choices. This was forcing some structure onto our problem. And the structure with how we were modeling this was that higher etas switched us from one option into the next. And then if we kept going, increasing our eta, we would move into a third option. So sort of like we had to separate the latent space into categories. And the reason we had to do this is because this was ordered choice. We weren't just picking our favorite thing out of a list of options. We were picking things in a particular order. We had to do this because we think there's some extra structure to something like a Likert scale. So if I'm picking from an ordered list, you know, I think our example is no choice. We had the basic, we had small upgrade, and then we had the premium. In this environment, we were, you know, we sort of assume there's some structure to this. In general, people are not going to go from no choice to small upgrade to basic. If you just, in terms of preferences, like, if you're thinking about, like, look at me, I'm so put together, yeah. I'm a professional, I promise. Like you can think of like price per util, and in price per util, this may be unordered, but the basic like preference, if I were to give you these things for free, you would rank them in this order. This was the core setup for what we tried to do last time. I think the ordered model is less intuitive and less sort of generalizable than the kind of thing we're going to do today, which is when we have an unordered list. And this is, an unordered list is essentially, I'm just going to give you a set of things and you're going to pick from them. And I'm not going to impose any additional structure on your preferences. And in some ways, like, we can model this with the unordered list that we're going to cover today, the unordered set of models with what we're doing today. So this could be walking, biking, car, train, or airplane. If you're trying to get from two cities, these are 5 different options you can take. And what we're going to do is just assume that there is no, we're not going to assume that there's additional structure to this. But the basic framework is going to be very similar. Each one of these options has some unobservable utility measure that we're going to model, just like we did before. And then we're just going to pick the maximum utility. So instead of separating this out into regions and we pick the thresholds, which in my mind feels pretty unintuitive, all we're going to do is set up a horizontal axis. I think actually, I'm going to show you a different way of setting this up with a vertical axis, which is how we can include covariates. But for now, think of this as some latent space data. And all we're doing is trying to build a model to place each one of these options on the horizontal axis. So, of course, biking is always going to be the best. Is that right? No Laura agrees. And then walking is second best. I think the train and the airplane are pretty close, although train is even better. And then driving is by far the worst. No disrespect. So this is the idea, and then what we're doing in our unordered multinomial is setting this up so that the thing that you're doing is choosing the thing that you like the best. So the goal of what we're doing is to order, to set up a latent variable using predictors so that our choice is just the thing with the highest utility. Sometimes we call this the the random utility model. But the basic idea is we're sort of embedding the idea of a latent variable in sort of the conceptual framework that you're familiar with of utility and choice. Okay, any questions here?
So
What?
if you're trying to make this model for somebody else and you don't really know their preferences,
Yeah.
so I guess is that what we're getting to figure out today?
Yeah, exactly. So we don't actually ever observe eta. All we observe is different characteristics and then how people make their choices. So I'll show you some examples a little bit later. But yeah, this is just like before in all of the existing estimation procedures. This is essentially, we're just trying to estimate a y variable using predictors. And the y we're trying to choose is just which one of these things, or the y we're trying to estimate is just which one of these things you're choosing. And then we're going to use covariates to make those predictions. And it turns out this model we're about to introduce is exactly the same as our binary models from a few classes ago, except with more options. So if we only have two options, if it was only flying and taking the train, this would be exactly the binary models we talked about, where we're trying to predict some latent variable and then compare that to 0. So if one cutoff and we're picking the higher or lower thing. It's just here, the cutoff is determined by the utility level of everything else for us. So in some sense, like the cutoff is almost like dynamic. Okay, any questions here? Or any other questions, I should say? Okay, so I think this is one of the most interesting models we have. And what we're going to do is just set this up. So this is the random utility framework. There was a Nobel Prize given to McFadden in, I believe it was 2000, for setting up these ideas. So this is not a trivial thing in the field. And in some ways it's on the newer side. 2000 feels like forever ago, but in the scope of like econometrics, this is a relatively new idea. So the basic setup looks like this. We have some utility level, which is essentially our latent variable. We're trying to build a statistical model to set up some level of utility. We don't see utility directly. All we see are the choices. So this is the utility for option M for individual I. And what we're doing is just looking at the attributes. So XIM is a choice attribute. So this could be the cost for individual I for choosing M. So this is like some attribute of the object M, but we can allow it to vary by individual. So this is an example of an attribute. So for you, biking, like if you live in the suburbs, biking into school is going to be very costly for you. So your cost may be higher for the same transit mode. So this could be the cost, just like the physical cost of biking. And then beta, we're going to assume is going to be the same for everyone. We get this, what we call a common coefficient. This is essentially the cost and how it translates into utility. So in a lot of ways, this is very similar to like a core utility model, where really we're just we're thinking of how things like costs impact our choices. So this is our utility, and then we can have individual attributes, which will vary by individual, but not by choice. So this is there's no subscript zi here, but each would enter with its with a coefficient specific to the attribute m. So for example, if I'm increasing income, so let's say zi is income. If I'm increasing income, this may impact my choice of riding the bus. So this allows us to sort of think about something like whether the good is normal or inferior. So the impact can vary. Impact of an individual characteristic like income can vary depending on which product we're looking at. But as you can see, this what is this, delta or gamma? That's a gamma. Gamma m is not subscripted by I. So this is specific to the product. Okay, and then this last thing is the error term. So this is the individual I for m error term. So just an error on the utility. Okay, any questions here? As I'll mention, but not talk about in a lot of detail, there are ways of complicating this model, as there are with really any kind of model. You can add subtlety and complexity to it for your particular application. We're going to cover the simplest version of this, just so you have some experience seeing random utility. It's a very powerful framework. I'll maybe post an additional notebook on some of the extensions if you're interested. But this is just incredibly powerful as a framework. The reason this works, and the reason this has nice estimation procedures, is because we're going to make one particular kind of assumption on the error terms. This is not a particularly stringent assumption, but it makes the math very tractable. So part of the challenge with what we're doing is we're taking a maximum over different random variables. So we're introducing random variables into our utility function, which so each one of these things is, moving around simply due to randomness. And when we take the maximum of a bunch of random variables, the shape of the maximum of that distribution, the shape of the maximum over like an argmax, that's a challenging thing to do in general. Right? We take, let me just write this on the board so you can see it. So this is, so we're doing argmax over a bunch of things. So A, B, C, airplane, bike, car, walking, and train. Taking an argmax over 5 random variables, that outcome depends, the distribution of this argmax, so the distribution of this thing is challenging to know. And it depends on what the underlying distribution for these variables looks like. The key trick with McFadden and the random utility framework is that we assume the error terms of our model are distributed according to a Gumbel distribution. Has anyone seen a Gumbel before? the gumbel is almost comical in certain ways. But the reason we use it is because it has nice mathematical properties for this problem. Let me just let me just show you the PDF because I think it's almost comical. It's like, okay, we love exponentials. Let's raise an exponential to an exponential. Sometimes we call this like a double exponential. This is the only context I've seen the gumbel, not the only one, but it's like one of the only situations where I've seen the gumbel. Gumbel distribution. And does anyone else pay Wikipedia money? Okay.
But not consistently.
Okay.
I think they're lying about their financials.
Their financials are great, actually.
I'm saying,
Do you?
I pay them, yeah, just a tiny bit of money.
What? You guys pay Wikipedia?
Yeah, you can be like that.
Look, I grew up listening to NPR, pledge drives, so I'm maybe responsive to it. But I've used Wikipedia so much, I might as well just pay them a little bit.
I think it's gonna become the new it girl, especially with like
Wikipedia.
AI.
Yeah.
Wikipedia?
Yeah. I feel like growing up they were like never use Wikipedia, and now it's like shifting. Like all of my teachers in elementary school were like, this is not a reliable.
That's the way it was for me growing up when, like, I'm old enough that Wikipedia, I remember a time before Wikipedia. But Wikipedia at this point is more reliable than any other, even Britannica, because it doesn't update quickly. Anyway, so this is the from our favorite website, the gumbel distribution. This is what the PDF looks like. This is the CDF. The functions themselves, look at this. So this is the standard gumbel. This is e to the negative e to the negative x. It's like someone's like, okay, let's just make a really crazy looking object. What this does is measure extreme events. So this is a distribution that's set up to handle extreme events, which is what this is doing. The argmax over a bunch of random variables, because we're looking at maximums, is like it matches this this type of setup very well. We're not going to talk in a lot of detail about the gumbel, in large part because like we don't really need to go into a lot of depth, and like I think deriving the properties we're about to talk about isn't worth a lot of class time. But I just wanted to show this to you to give you some foundation for where this is coming from. In general, I don't like just showing you something without explanation. This is a model of extreme events. You can read through the description here. Thinking about like maximums, which is exactly what we're trying to do. And the core idea with McFadden is that this distribution, assuming that the error terms follow this distribution, allows lots of nice downstream results. And that's not because we've chosen this. I mean, we chose this distribution to match the problem, which is exactly what these kinds of things are set up to do, right? In some ways, we're imposing an assumption on our model by assuming that our error terms follow this distribution. But sometimes like the right assumption is like mathematically turns out to be just very, very nice. And in a lot of ways, that's what's happening here. You can use different assumptions. It's just the math doesn't work out quite as nicely. So that's what we're seeing here. Any questions about this? This is one of those cases where I'm going to like only partially justify where the gumbel comes from. I think for everyone's benefit. We'll do a little bit of justification, but not the full derivation. If you're interested in that full derivation, we can chat about it. So our error term, which is what's left over after we've modeled utility, is following Gumbel. So you can sort of think of like the Gumbel distribution is generating the extreme events for us. This is the only context I've ever used a Gumbel. I don't know, I've taken a lot of statistics classes and taught a lot of areas of statistics and use a lot of statistics in my work. And this is the only one I've ever seen a Gumbel, which is fun. Okay, so we assume a Gumbel. What does that get us? It gets us this thing. This is what we call the softmax. We're saying the probability that our choice is equal to j is essentially a logit, just in a more general form. We use softmax. Did Andy talk to you about neural networks? Did he talk about softmax?
You mentioned it, but we
Okay.
didn't talk that much about it.
Nice. Yeah, sometimes neural nets, at least the original ones, used softmax. I think the industry has shifted over to a similar function, just sort of doesn't have, it's not wavy, it's just a bunch of lines, called ReLU. Did he mention ReLU? Okay. This is the softmax. What we're doing is we're taking each of the utility levels. So we're going to estimate a bunch of essentially betas. And again, unfortunately, my notation will change a little bit. But our utility function, the utility level for individual I for option J, what I'm going to denote as V. So Vij, we're going to raise each one of these options to the exponential. So it's e to the level of utility. What this does is it turns everything into a positive number. So raising something, it could be positive or negative. We're going to raise it to a positive, we're going to exponentiate it, which will return a positive number for us. So each one of these elements here is a positive number. To generate the probability that we choose option J is has this exponential in the numerator. But then to standardize our probabilities, to turn this into a probability so that the sum of all of the probabilities over every option we have available to us sums to 1. We then divide each of these by the sum of all of the utility levels raised to some exponential. So this is just turning any number into a positive number, making the extreme ones more extreme. And then this, the denominator is just normalizing it so it is a probability. That's what the softmax does. And it turns out the reason we're using the Gumbel is because this assumption allows this thing to have nice characteristics. We sort of get this for free from the Gumbel. That's the part I'm not going to talk about in class. If you have more interest, we can go through and derive this in my office if you like. But these are sort of two sides of the same coin. And McFadden chose this so that we get this. Any questions here? Look at this. What does it mean to ald something? I'm not sure. Who wrote these slides? Me. I did. That joke always works for the undergrads and seems to never work for you. So, are you just tired? I see you. Okay, so that's the basic idea, and then just as a reminder, we're in this latent variable framework. The yi is the thing we're choosing, but the vij or in the notation of what we've used before, the eta ij is just the sum of a bunch of characteristics of the object we're choosing, and individual characteristics for the chooser, zi. Okay, and let me just, I think my goal is to just basically set this up at the beginning, some of the core conceptual ideas, and then we're going to walk through the building of the thing. But to really get what we're doing, you have to understand this part. This is the probability of choosing I. The probability that our choice, yi, is equal to j. This is the notation for choosing the thing. This is going to be a probability. Our model is truly about probabilities. We're translating this latent variable into probabilities using the softmax. What we're doing with the softmax is taking the utility level, which is constructed using the parameters. So we're taking the parameters and putting them into the exponent of each one of these exponentials in the softmax. So if I were to write this out in full, I would see these elements inside of the exponential. So we have the betas and the deltas all inside of this softmax. And then we're trying to choose the parameters so that the error, the miss between our model and our observations is as small as possible. And the way we do that is with a likelihood function. So then our entire objective is to take this thing and choose the betas, the parameters, so that our model misses as little as possible. Okay, I think if you get this much, the rest of this class is going to be pretty straightforward. At least that's the hope. But all we're doing is trying to pick the betas. The beta enters inside of the numerator and the denominator across all of these options. Okay, and then we're just going to define a likelihood function and maximize it. All right, any questions here? We're so deep in the semester, but this is like truly one of the big ideas in estimation. Okay, so nice. I mentioned this before, but the two alternative case is exactly the same as the binary logit. And it just looks like this. This is really nice in a lot of ways. There's kind of one downside to the basic version of this. In some ways, do y'all know independence of irrelevant alternatives? IIA. We talk about it primarily in like social choice. If you're familiar with like, the way I'm most familiar with this is in like Arrow's impossibility theorem. If you've heard of that. Anyone heard of that? Okay. It's essentially telling us like if you change something comparing two alternatives, it shouldn't change. Like if it's just about these two alternatives, it shouldn't change the rankings relative to other things. And the core model of random utility embeds this this set of ideas. Okay, we'll come back to it a little bit later if we have time. So we're just going to basically set up a synthetic data set. I'm going to get out of the slides. And this is, hopefully going to feel pretty familiar with the kinds of things we've done before. All I'm doing is setting up a random seed. We're going to have these parameters. We'll set up a bunch of true alphas. So these are our parameters and a beta. And then all we're going to do is draw a bunch of data here. So I'm going to run this. We're going to simulate some utility. So these are just the error terms from a, let's see, no, these are the uniforms, and then these are the Gumbel errors. So these are the errors. And then our choice is just going to be over, it's just the argmax of a bunch of alternatives. And that's going to give us our choices. So this is all a bunch of simulated data. Let's just take a look at the shape of these things. So this is, we have 3 different utilities. So we're choosing over 3 different things, 3 alternatives, and then 2,000 individuals. So these are the utility levels for each thing, our vsim. And then we're just creating some error. So these are 3 utilities. You can think of these as like 3 different transit modes. And then we're introducing some error. So like everyone thinks randomly. Like I woke up this morning, I was half tempted to walk to school. I didn't, I usually bike, but sometimes I walk. Sometimes I take a bus. I never drive because driving is clearly the worst of all transit modes. I guess sometimes I do take a lift though, so, but only when it's raining. So this is sort of the basic structure, right? So we have 3 different utility levels. These are going to be generated with error because of this uncertainty in our decision making. And that error, as long as we assume it to be Gumbel, looks really nice mathematically. So then this is the y sim is just the simulated y outcome, which is just after we've introduced the error and we've looked at the utility level, we just pick the thing we like the most, which looks like this. Any questions? Does this feel pretty straightforward? I think none of the steps are going to be that challenging. It's just the reason this won a Nobel Prize is because it brings together a lot of powerful tools in a really nice framework. But yeah, the core ideas are relatively simple. Okay, so nice. So we have this. We could also plot, y sim, which is just a choice of our different options. So this is, the different outcomes. And all we're trying to do is our main objective here is to write down a likelihood function so that we can plug it into an optimizer. So you can see the building blocks here. We're going to write down the likelihood function, which we know the way the data is constructed from Gumbel. And then we're going to construct the likelihood function, which is just going to be, or the log likelihood function, which is just going to be the sum of the log likelihoods for each alternative across individuals. Okay, so there's a bit of unpacking here, but the basic idea is we're going to set up the deterministic component of the utility. So this is v plus r alpha. So this is this thing, which is 3 different intercept terms. And then we're going to multiply our beta by some set of predictors. And then this step here, just to make sure we all understand what's going on, what we're doing for mathematical tractability is I'm going to subtract off the maximum of the utility for each individual. So I've constructed a bunch of utilities for each individual. If I just subtract off any number, it doesn't change the ordering. So if I shift everything up by 100, or shift everything down by 20 million, it doesn't change the ordering. So my choice isn't impacted by subtracting a particular value. It's sort of like utility numbers don't matter. All that matters is the order. That's what we're able to do here. I'm doing this for mathematical tractability, or computational reasons, I should say. So I'm just taking off the largest value. This sort of puts us sort of right around 0. It essentially, it puts everything just below 0, which is totally fine. And then what I'm doing here is then just constructing the probability for each option. So this is for the chosen V. I'm just looking at the V, and then I'm looking for the particular chosen one. Should we call it Harry Potter? And then thank you. Or I'm sorry. And then this is for the denominator. So this is just looking at all of the options and then taking a log over their sum. The reason, so then we have the chosen V minus, so this is the log for the particular log likelihood. This, because we're taking the log, and we're taking the log of the softmax. When we take the log, it's because it's the ratio. It's the log of the numerator minus the log of the denominator. The numerator is raised to an exponential, so it's v. So we have the log of the exponential of v. But the exponential and the log cancel, so all we're left with is the v. So this is the v of the chosen alternative, minus the log of all the things in, it's the sum of what's in the denominator. The log here doesn't cancel because it's the log of the sum of a bunch of exponentials. So we have to, we can't do any simplification here, but we could do a simplification in the numerator. And then we're just doing this, and then we're summing over all of the alternatives. Okay, any questions here?
So the log and the denominator, and how do you interpret that?
Yeah, so we'll come back to interpretations. You mean of the betas? Yeah, so we'll come back to the interpretations a little bit later. This is going to be about as challenging as like with binary models. So your intuition for like the difficulty of interpreting the coefficients is going to translate almost perfectly from the world of binary outcomes into this world. So it becomes kind of challenging. There's going to be one extra step we'll talk about, which will make it a little bit easier. But yeah, with nonlinear models, interpreting the estimates is just a challenging thing to do. Okay, any questions here? So this, I think, is the hardest maximum likelihood we've done so far. But I think none of the steps are too incredibly challenging. The next thing we're going to do is just minimize this. Or maximize the likelihood or minimize the negative log likelihood. So here I'm just creating a negative function and then putting it into the optimizer. And then this gets the main results. So let me just initialize this. And then we'll run we'll run this. Theta hat is not defined. Oh. All right. So here are the estimates. And if we compare these, they should match up. So our the true ones are here, listed in the first column. The estimated one is here, and then these are the standard errors that we constructed using so the Newton-Raphson, the fancy version of the Newton-Raphson gives us the estimated inverse Hessian, and then we can just use that for the standard errors. And this is the set of results here, and you can see that the truth and the estimated are very, very close, and even in the context of these very small standard errors, we're basically right on it. Okay, so any questions here? So high level, what we're doing is we're using the softmax and this idea of the utility function entering the softmax, and then constructing the log likelihood using the softmax, and then we just estimate the log likelihood using MLE. That's it. At least the core model. So what I've shown you here is nothing particularly interesting. This is just to verify that the approach we're taking recovers the core model. And remember what we're doing above is we're basically generating the same kind of thing as what we would like in practice. We have this deterministic utility part, which is made up of things that are, relative to, like, they're like predictors of the characteristics. So it's like, how costly is it for me individually to bike? Well, I live 2.5 miles away, so it's not that costly, and they're bike lanes away. If you lived in the suburbs, your XIJ for biking would be very high, where for me it's very low. So the individual characteristics for the attributes can vary. So that's what we're estimating in betas. And then in alphas, we're just giving different scales. So we have 3 different alternatives. So we have 3 different intercept terms, one for each of the 3. And if you were to look at this, this V is just it's a big matrix, 3 units wide, and 1 for every individual in our data set. So it's giving us 3 different set of characteristics for each of the 3 alternatives, and it's doing that for every individual, which looks like V sim. So it looks like this. 3 different utilities, and then we're trying to predict them using the we're trying to predict this using the attributes. Okay, so X sim. So these are our attributes. Okay, everyone on board with the basic setup here? I think at first glance, this looks pretty similar, and then at deeper glance, there's some nuances, and then beyond the nuances, everything again looks pretty similar. But the basic setup that I want you to understand is how the data sort of looks, how we map that into a maximization procedure, and then from there, we're in the world of things we've done before. Okay, I'll take that as everyone's on board. So this is and what I'm showing you here is just that we've done it. Like, we've gone through, we've set up the MLE correctly, and then we've estimated the thing, which is giving us true parameters that are very close to, or estimated parameters that are very close to our true. Okay. So the next thing we're going to do is actually estimate using some real world data. What we had done in our simulated version assumes by construction that the error terms are Gumbel. But what we're going to do is take this to some real world data and actually perform an estimation on Montreal to Toronto transit. But what if we take a break first? Would that be nice? This is maybe a good break point. So we'll come back in 10 minutes and, or 12 minutes. Let's go to 10:15, and then we'll talk about a specific application. And we're going to go through this a little more quickly. I want to show you some of the things, but there's also a lot of data wrangling that I just don't want to cover in class. All right, 10 minutes, 12 minutes.
get more confusing.
Have I showed you this picture?
She actually is like the cutest baby I've ever seen. I feel like most like newborns, they just look like
Really ugly.
ugly, but she doesn't. Ugly, but they just don't look.
They look terrible.
They look like aliens.
Yeah.
Yeah.
90%.
Yeah, Maxine is. This was on her first full day of life.
My parents took a vlog.
What's that?
My parents like vlogged my birth.
What?
Yeah. Because then I came out like on a. I was a C-section, so I came out on a wave. It was pretty cool. Yeah. I've watched like part of it, but honestly, I'm not like great with. Yeah. You know, they're pretty gross.
Yeah.
Birth in general, so.
It's
I
like,
got a little squeamy watching it, but it was fine.
wow, that's really cool.
Yeah, the habit is cool. But
Yeah.
I don't know if I actually want to see it again, but
Yeah,
it's nice to have it, I guess.
totally. I think if I could have a video of her being born, I'd be pretty into that, even if I'd never watch it.
Yeah, just to have it. I
Yeah.
think it's nice.
Oh my goodness, I made that one time. Never again. Let's see. Those are some old ones. This is 4 generations. Maxine, Molly, Audrey, and Annabelle. That's an amazing photo. Are you here for economics or for pictures of the cutest baby you've ever seen? This was Halloween. A long time ago.
Is that a specific duck or just a duck in general?
So we went as Bert and Ernie, and then this is the rubber ducky.
Okay,
Yeah. So specific duck.
yeah.
And then, look, I'm wearing the same sweater. This was. Have any of you been to Dad's Dog and Burger in Bloomfield? Kind of a new place. We went there one time, and Maxine needed food, and we just put her on the table. I died from cuteness. And then, yeah, we could keep going through these things. Or we could talk about Montreal. Anyone been to Montreal? Nice. Lovely place. They have some of the best croissants I've ever had in my life. We went up there 2 summers ago, I guess. Stayed in an Airbnb right on. They shut down major sections of the city for car transit, or for car through traffic. So they're just like massive pedestrian malls. They have great trains and great bike infrastructure. So yeah, we'd wake up in the morning, walk outside to the park, and there'd be like an outdoor bakery, or it was indoor, but it was like on the park, making fresh croissants all morning, and you could just get one, sit at the park, and watch the birds. It's amazing.
Did you go on Ferris wheel?
No.
Did you see it?
Yeah. So we, that's near the.
It was like an old. It was like I don't fully remember everything about Montreal, but
Yeah.
it was like near the old area, like the older district.
Uh-huh. Yeah, I think we went past it, but we didn't ride it. Also, I've been to Toronto. We went through Toronto to get to Montreal, and then I was back in Toronto in the fall. So, yeah, let's talk about transit. So the the most challenging thing with what we're about to do is just understanding how we set up this model. So I want to walk you through the data. We're not going to walk through the sort of the data manipulation components, but I want to show you what the data looks like, and then we're going to set up the likelihood function. And I think this will go pretty quickly. I should have run back and got my... can we extend... I just want to make sure my computer doesn't crash. Like 3 minutes of the break, and then we're going to do this. I need to run back to my office.
Dude, you aren't even into it yet. It gets so much more confusing. It's also like, who are these people? It's, why are we going back in time? It's, no, it's a lot. Yeah, no, she's just kind of accepting it. She's just like, okay, that's what I stayed in this haunted house where she's crazy.
Okay, so we have 4 transit options, and we have a bunch of covariates that we observe. And then we also observe whether the individual chose that, that transit option. What we're going to do for sort of comparison reasons is only look at the cases where all of the data is, all 4 transit options are available. But just to give some definitions here. So for each individual, we have their income, and we have an indicator of whether they live in an urban area or not, which will matter for some of the comparisons, right? If you don't live in an urban area, buses and trains are just not that prevalent. And then, so these are the characteristics across individuals. So as I'm going to show you, this is for one individual, but then we also have multiple transit options. And what we need is we need a bus cost. So the cost for individual I to ride the bus. Then we also need the cost for individual J to ride a bus as the transit between the two cities. But then we also need the cost for individual I for taking the train between the two cities, and the cost for individual j for taking the train between two cities. So we need a cost that's individual to the specific to the individual and specific to that individual taking the particular transit option. So this is subscripted by the type and by the individual. So we need one of these per individual transit pair. In vehicle time is like the way I understand this is how long you were in the vehicle for the transit time, and then this is how much you were like waiting or whatever, so outside of the vehicle, and then this is like a measure of how frequent the service, which isn't going to be so relevant for the car, but will give us like a measure of speed for the other options. Okay, any questions here? So the outcome variable is choice. So we're going to set this up as a binary at first, but then we're going to, I'm not going to show you all the steps, but we turn this into a multinomial outcome. And then, so this is the basic setup. Case is the ID. So this is what the data set looks like. So this is essentially an individual identifier. And let me just walk you through each one of these rows. Because I think actually understanding what we're doing with this model depends on understanding the structure of the data. So we have the individual ID. We have the alternative that's available to them. And then we have their choice. This is going to be 0 if they don't choose the thing, and 1 if they do choose. This is the distance between the two cities. And let's see. I don't remember if this is different by individuals. So dist dot. So yeah, I guess it is different. Even though you live in the same city, sometimes like your location in the city will differ. So this is just a measure of how far you're going between the two cities. So you could go from like far suburb to far suburb between the two cities, or downtown to downtown, or close suburb to close suburb. So the distance can vary. This is the cost for the available transit option. So what's amazing about this data set is we observe the cost not just for the thing that was chosen, but also for the thing that was not chosen, which is part of how we can estimate this model. So cost being one of the predictors. So this is the in-vehicle time, and then this is the out of vehicle time. And you can see because cars go point to point, they have 0 out of vehicle time. They're not the fastest. The flying is the fastest, but they do have the least out of vehicle time. Okay, so this is the basics. This is the frequency of the transit. So I don't remember exactly how this is measured, whether it's service per day, which might make sense. I actually don't remember the units here. And then this is a measure of income. So this is how much the family is making. And I'm assuming this is in thousands of dollars, thousands of Canadian dollars. Loonies and toonies. Thousands of, or half thousands of toonies. And then this is the binary for whether they're in an urban setting or not. We just used the number of alternatives to select only the the individuals where all 4 transit options were available. So some people might not have access to a car, and we want to exclude them. And the reason we do this is just so that we can properly estimate the relative utilities across these alternatives. Okay, any questions here? So this is fine. The reason there's a bit of extra work is because this is set up, you're familiar with like panel format structures. This is in long format panel. And what we actually want is for each row to represent the choice. So we need, because we have 4 rows per individual, we need to sort of reformat it so that it makes more sense. So that's the thing I'm not going to talk about. That's what all of this is for. And once we do the restructuring, this is what the choice looks like. So here we have, a bunch of zeros. So this is the person choosing the 0 option, which is the train, or not choosing the 0 option. And then these are the people choosing the 2s. So that would be bus, I guess. So that's the basic structure here. This is an array with the chosen transit mode. Any questions? You can also look at, so I've broken this up into predictor variables. So this is income. This is some of these. So this is like cost, frequency, out of vehicle time. And here you can see that the structure matches what you would expect. So this is, 3 different variables. And then we also have in-vehicle time, which looks like this. So this is, the 4 different modes and how much time they're spending in each. Okay, any questions here? This is just setting up our data so that we can ask the question. And then I have a bunch of helper functions. Again, these are not particularly useful on their own, except for these 2, computing utilities and the log likelihood. So the way we're going to set up the utility for, the way we're doing this, we have a VIJ for each individual and alternative. And let me just, I think in this context, it's much easier to understand with a bit of math. But the math I'm about to write down is what this is doing. And it's been like an hour since I showed the softmax in the slides. So let me just write this down. We have the We have the probability of choosing for individual I choosing option J, which is the exponential of the utility associated with option J for individual I over the sum of all of these things. So this is for individual I, we're going to look at the sum over all of the different J options. So this is E to the V, nope, this is bad notation. Let's do over K. So we're just looking at all of the other options and finding the softmax. This gives us the probabilities, and what we're trying to do is estimate the model that goes into these probabilities. In this specific example, we want the probability of the car. And we're doing this for each of the 4 alternatives. So this is the utility for the car. And then we're looking over all of the transit options down here. So this is for K in car, air, train, and bus. and then we're just summing up the utility for each of these. This thing is what gives us the softmax. For each individual, we actually need 4 of these things. We're taking the log, so the likelihood function, the log likelihood function is essentially summing over each individual. So this is the sum over each individual I. But then we need this thing for each of the 4 transit options. So one way of writing this is for each of the different, should we call these transit options? Sorry to switch the notation on you. So the transit, sum over the different transit options. And this is the probability of choosing that transit option. So this is a bunch of individuals, and each one has their own transit alternative that they're choosing. I'm going to write this out more explicitly because I think seeing this makes it even clearer. And I should say this is the log of the transit of the probability. So this is the log of the probability for individual I choosing the car plus the log of the probability of individual I choosing the train. I'm going to skip one, and then we go to the log of the probability of individual I choosing the bus. Each one of these is the log of the softmax. So this is, this thing here is VI car minus the log of the sum of the different transit options. So the sum of the probability I of t. So this is like a massive nested function, right? There's a lot going on here. And we haven't, in this thing, we haven't even written out the betas yet, right? The core idea is that we're trying to construct a utility function that maximizes the likelihood at the observed data. So this is the whole thing. And I think getting the conceptual framework is more than enough. To write all this out, to understand like the structure of the thing, even though this is pretty complex, allows us to construct the log likelihood function. This is just to compute the utility for individual I for the alternative j. So this is basically just behind the scenes constructing these things. This is just a helper function which allows us to do that from the data. Then for the log likelihood function, we're constructing a bunch of v's, and then we're normalizing it, and then just going through and adding up these things. So this thing I've highlighted in the code is just this thing. Just basically double summation over all of the alternatives for each individual. And then we're trying to use the the maximum likelihood to estimate the betas, which go into the VI's way.
So individuals, you think everyone in the data set, or like
Yeah.
multiple? So one person.
So this I is for different people making the multinomial choice. And then we have 4 different alternatives, so then we're summing over those. Okay, any other questions here? Okay, so nice. So that's what this is. And then, let's see, let's make sure we run it. That's about all I feel like I need to talk about this. And then what we're going to do here is just maximize. which is going to give us some results. This says it didn't converge, but I was playing around with this. The reason it's saying it didn't converge is just because the slope is really flat around this point. But these are at least the way I've set this up, these are the correct, this is the correct likelihood. It's just that the curvature is very flat around the solution. You could play around with different, like this might benefit from, I'm not going to change it in class, but there's a log version of Newton-Raphson, which you could try. Okay, so nice. So this is the log likelihood. And then here I'm just getting the standard errors from the Hessian. So we get standard errors for free from the Newton-Raphson implementation. And then I'm just going to get the parameters. Okay, so this is just the thing we've gone through and estimated. I have both the point estimate and the standard error for each one of these. And you'll remember behind the scenes, like some of these are individual specific, right? Like changing income will change your the estimate for each one of the options. Because like if you get more money, you're going to take the fastest one. If I like 10x your income, you're going to fly whenever it's faster. And that's going to have a different impact than taking the bus. Personally, I love the bus. No matter my income, I will ride the bus. But I think in general that's not true. The bus is a little bit slower. And maybe I wouldn't take the bus between cities. Maybe I'd take a train. And then income. So the basic idea is that we want the income effect to be different for each of these. And then we exclude the train. So we're essentially like comparing the income effect of all of these things relative to the train. And then, so we do all of these things. So some of these are specific to the transit mode. Some of the, like this, so the intercept needs to be specific to the transit mode. And then some of these are going to be, these are like in vehicle time. When that changes, that will have a different effect by transit mode. But then some of these, like the cost, we're just going to say is the same across all of the options. So if the cost goes up, we want to understand something about how we change our behavior with the different sort of across the different modes, but constant. And then frequency, and then out of vehicle time. Okay, so a couple of things to note here. Well, before we do that, are there any questions? This is amazing, right? Yeah, the answer is yes. This is not a lovely table, but this is a lovely procedure to be able to run. 50 years ago, we couldn't do this. Like in the scope of things, this is a new procedure. Okay, so just to take a look at a couple of these things, this is positive, as you'd expect. So if you get more money, you're going to fly more relative to the train. And then relative to the train, as income goes up, you're going to ride the bus less. But you're also going to drive more. Okay, if only this were negative. My dad visited this weekend. He lives in the suburbs and drives everywhere, and is very unconvinced by like pro-transit arguments. So it's a fun conversation. We always get into it. It's exciting. Okay, so this is nice. And then in vehicle time, weirdly, this is a little, so relative. This is not relative to anything. This is just the longer you're in the airplane, the more you're likely to fly. So this is maybe a little bit, I'm not sure where that's coming from. But the rest of these are negative, which makes intuitive sense. Okay. Any other questions here? So the directionality of this is nice, but often we want something a little bit better. So it'd be nice if we could interpret what we're doing sort of like we did with the binary models where we used average marginal effects. Here, I think we could do the same thing we're about to do with the binary models. But I think the interpretation of multinomials allows us to make sort of elasticity kinds of claims a little bit more nicely. So this is just, this is the first derivative, which gives us something about how the probabilities change when we move any one of the predictors. In OLS, these were exactly equal to beta. But just like with all of our nonlinear models, and I think the best analogy is the binary outcome models, the first derivative depends where you are. So the impact of changing any one of our covariates is different depending on what the baseline probability is. And this makes interpreting the point estimates of the parameters pretty challenging, just like in all of the settings before. But the standard method for the random utility model is a little bit simpler, actually. You remember the definition of elasticity? Just the slope, and then we multiply it by, it's like the change over the ratio, so the baseline. So the calculus definition of the elasticity looks like this. When we take this definition and we apply it using these first derivatives, we actually get something that's a little bit nicer than before. So the way we're going to interpret the results, the point estimates, is essentially as an elasticity. The reason this is nice, or one of the reasons this is nice, is because it allows us to have a unitless measure. So sort of give us sort of constant, like unitless elasticities, but it also allows us to interpret some of these things a little more directly. This is still a little complicated. Let me show you. I'm not going to talk you through this, but this is essentially translating the point estimates into elasticities, and we can do that for the own elasticity. So how the x changes our probability of using whatever transit option we're considering. But we can also think about how, so that would be something like the cost of an airline goes up, the flying goes up. How does that change how you fly? But then we can also think about how, which would be the cross elasticity. You can also think about how the cost of an airline going up changes how you ride a train. So we want some measure of both of those things. So we have the own elasticity and the cross elasticity. And so what I'm doing here is just calculating elasticities. So this, because it involves the point estimate, this gives us a very nice interpretation using the point estimate of like a way of interpreting our model using the point estimates. So here I have a couple of things. So these are the elasticities essentially of market share. So how does market share move with respect to changes in the x. This is the cross elasticity, and then the own elasticity, and then the cross elasticity on average. So these are like averages over each of the points over each of the predictors on average. And what this allows us to do is sort of make consistent claims. So these I think are a lot easier to interpret than just the betas directly. So anyway, this is useful. I don't want to get into the weeds too much on this, but this is useful for turning our point estimates into something that's easier to interpret and communicate to an audience. In a paper, an elasticity tells us the percentage change when we move our coefficients. Any questions here? All right, so this is nice. This is pretty deep in the weeds, but this is really good stuff. Like, this is a great way of communicating elasticities. Part of what you'll see here is that this is giving us a cross elasticity for each of the other alternatives. So this is just sort of an average impact for how changes in the one in air travel, for example, would impact all of the other options directly. And what's interesting here, and you can sort of see this in these outcomes, is that we're basically building into the structure of our estimation procedure this idea of identical substitution in elasticity terms across different transit modes. So what this bakes in by default is that doing something to increase the airline ridership. So to decrease the airline ridership means we increase the ridership of the other transit options equally across the board. This is how we bake in this idea of independence of irrelevant alternatives. So if I decrease airline ridership, that should have no impact on the relative ridership across the other alternatives. So if I take the airline out and compare only the relative ridership across bus, transit, and car, if I take airline out, that the relative share of those three other alternatives should not change. That's the assumption of IIA, and the default model builds that in, which in some cases is reasonable. In this case, I think you could make a claim that it's reasonable, but there are lots of examples where building this in is not reasonable. If I include this is the thought experiment. If I have three options, flying or taking a red bus, and let's say I split those evenly. If I include a third transit option, which is riding a blue bus, the IIA assumption, and let's say when I add the third bus in, we split it evenly between all three alternatives. The IIA assumption enforces that the red bus and the airline will still have equal share. So I've added a third bus, a blue bus, and that's that's increased the total bus usage. And this is obviously like very unrealistic. The reason is because there's specific substitutability sometimes between alternatives. So if I add another bus alternative, that's a substitute directly for the existing bus and less a substitute for the existing airline. So if you think there's not much even substitutability across alternatives, the IIA assumption is very nice, but it's an assumption. And if you think there are differences in substitutability across alternatives, the IIA assumption is less desirable as a property. Okay, any questions here? My feeling is that we skip IIA. This is, we think a lot about this in economics. It's one of the core, it's like indecision theory and social choice, and it shows up in these kinds of models. Like we have to think about whether we think IIA is a useful tool. Okay, so I'm not going to spend too much time on that. Feel free to take a look if you like. But you can think about whether this seems realistic or not. Okay, the last thing I think I want to cover here is with predictions. So this is a really nicely structured model, right? We're making choices. We're thinking about modeling choices over many alternatives. And just like with any statistical model we can construct, like you can make counterfactuals. This one is just really nice because it's doing a lot of stuff, like this whole thing. So we can actually make strong counterfactual claims. And the way we're going to do this is exactly as you'd expect. Nothing particularly novel here. It's just we're going to take the predictions. So I've just used the model to make predictions using the function predict shares, which we defined up above, right here. So I'm just computing utilities at some given levels, and then returning their probabilities. So what I'm doing here is just measuring predicted shares using the estimated values. So I'm plugging in the predictions using the estimates. This is using the estimates we constructed, but we can also, in addition to just predicting the probabilities, we can move those predictions around and check what happens in a counterfactual world. So this is just, this is exactly identical to how we think about making predictions using like linear models. All we're going to do is look at a different point on the domain. So that's what we're going to do here. This is a type of counterfactual. So what if I improved the speed of a train, but I made it more expensive? So we switched to like a bullet train between Toronto and Montreal. Come on, that would be amazing. So we're just going to build in a faster but more expensive train. So all I'm doing is taking the original in-vehicle time for the train, and I'm dividing it by 2.5. So this is going to be a much faster train. But I'm also going to make it more expensive. So I'm going to multiply the cost for the train by 3. You don't have to follow all of this code. There's a lot of machinery to make this happen. But essentially all we're doing is just swapping the estimate, swapping the actual value by 3. We've done the estimation, and now we're just swapping the data. And then we're just going to use that swapped data where we've made the train faster but more expensive, and we're going to plug that into the model that we just constructed. So we're changing the data and plugging that changed data into our model to give us predictions using the sort of counterfactual data, which is the same thing we do when we move, like when we make predictions using a linear model. We move on the horizontal axis and then check the prediction at a particular point of x. Here we're just doing a different one. Okay, so when I run this, I get the original estimate. So this is with the core data, the data from the data set, and then this is from the manipulated data, so the counterfactual data. And here we can make claims about how the different transit modes have changed. What I've done here is turn this into percentage points. So this is, the original is in terms of share. So this column sums to 1, and this column sums to 1. And the differences are pretty small. So what I've done is just multiply by 100 to turn it into percentage points. And so what you can see is when we make train, my transit brain is protesting. When you make the train much, much faster, but make it more expensive, train ridership goes down. People switch to other alternatives, which tells us something about how income and time preference relate to each other. So this is just one indication of the kinds of things we can do with these models. When I see this, I think obviously this deserves, like building these kinds of models deserves all of the accolades that it got. This is like a really powerful kind of thing we can do. When I'm thinking about like decision making, this is one of those like pinnacle kinds of models. We don't need this for most problems, right? This is setting up a latent utility framework to give us horizontal positions over multiple alternatives. And then we have all of this to estimate with maximum likelihood. But in general, when you're building statistical models, most of the things we do are either binary outcomes or we're trying to predict a numerical outcome. But when we have discrete choice over multiple alternatives, this is an amazing tool to have. Okay, and gives us these powerful counterfactuals, embedding like substitution between different transit modes and preferences for time versus money and all of these kinds of things. A very, very rich model. Okay. Any questions here? What if we cut the transit time into thirds? So still, if you tripled the cost and cut the time into a third, it's people still switch away. So this is, I think I've said how much I like this already. So this is nice, and then I just have a nice little visual here for the counterfactual. Buses don't change much in that world. Okay, so this is about the end. This is used pretty heavily in industrial organization. So if you're thinking about, these complex sort of market decisions, especially when it's more than just two alternatives, there's a pretty well-established literature on this. I think some of you will end up going into this kind of field. And this class will not give you the full treatment on these kinds of things. Like, we're spending most of a day on this. But I want you to be aware of these kinds of models. There was a really famous one of building a sort of a game theoretic structure around multinomial choice. I think the original paper, it's been a while since I've seen it, was on like pricing strategies for gasoline, where there's like game theoretic, like monopolistic, oligopolistic competition between gas stations. And so you can do just so much with this. So just know this exists and know the basics of how we construct these models. I'll ask you to do a little bit of this in the checkpoint on Friday, and there's a whole lot more to do. So if you're more interested, I can post a more detailed notebook on the extensions to this model. But I think this is enough for today. Any questions here? Okay, so maybe this is the one that you put in your earbud when you need to go to sleep. No, this is the pinnacle in a lot of ways. Like this is really one of the peak models. Okay, so let's see. I think we'll leave it here with multinomial choice. Let's take like a 3-minute break, and then I just want to come back, change gears a little bit, and talk about sort of a practical but less theoretically interesting application of data with APIs. So go remind yourself that you're a human being, say hello to someone, walk around.